Fat. The last major component of food is fat. So when we talk about fat, we're really talking primarily about these things called triglycerides, in which three fatty acids, which are the things here in red, react with one glycerol molecule over there in green and form sort of a three sort of legged thing. Right? This is the nature of these triglycerides. There's three glyceride molecules, these long chain fatty acids that make this whole molecule fairly nonpolar. There's very little oxygen or oxygen in these molecules after these have reacted, so that this whole thing is only can exhibit nonpolar interactions, or these van der Waals forces, which makes these not really interact well with water. And we expect that when we talk about fats, things like oils or butter, for example, that have a large amount of fat in them, they do not dissolve readily in water because the interaction between these types of molecules and that hydrogen bonding favor of water does not mix well. So when we talk about this, we can talk about something that's very nonpolar, which is going to have a very different set of properties than the things we've talked about before. Also, depending on the lengths of these chains that are inside these fatty acid chains, we're going to have much different characteristics. If we have really long chains, that's going to experience a lot of interaction with other molecules, which is going to make it sort of stick together pretty well, which is going to make it a solid. If it has fairly short chains, or there's a lot of places that disrupt that interaction, it's going to be more likely to be a liquid at room temperatures. So all of these things play a factor of these basic ideas of these triglycerides. One thing when we talk about fat that we always sort of need to discuss is this idea of saturation. So when we talk about saturation, we're talking about how many areas of double bonds do we have in a molecule. So if we look at this first one, again, this would be a fatty acid chain inside of these triglycerides. They could be mixed together, it could be separate ones. But if we have all single bonds in this molecule, where every bond is between a hydrogen and a carbon, or a carbon and a carbon, all single bonds, we refer to this as a saturated molecule. It's got as many bonds as it can have, as many hydrogens around it as it can, so it is saturated. It's completely happy. It can be fairly unreactive, and therefore fairly, it's the places where we get this interaction, this van der Waals interaction, is going to be large. So things that have a high amount of saturation, or are highly saturated, are going to be those fats that we consider solids at room temperature. Things like lard, animal fat, shortening. All of those are going to have a high degree of saturation. We can start then taking away some hydrogens to make this unsaturated. And if we only have one place where these hydrogens have been removed and formed a double bond, or one double bond, we call that monounsaturated fatty acid. So if we only have a small amount of hydrogen lost, some removal of this hydrogen to form double bonds, we get these monounsaturated. If we have several, then this is a poly unsaturated triglyceride or glyceride. So this degree of saturation really plays a role in how many hydrogens are in this molecule, or how many double bonds. The more double bonds we have in these fatty acid chains, the more unsaturation it's going to be present. And this plays a role because the degree of unsaturation is going to have an effect of both the chemical behavior but also the physical behaviors, as we said. Things that are fully saturated are going to tend to stick together better and going to be solids at room temperature. Things that have a lot of unsaturation, they're not going to be able to stick together as well, and they're going to be more likely to be a liquid. Those things that have oils, like olive oil and such, have a large amount of unsaturation in them. You probably heard a lot about this idea about trans fats. That comes in this degree of unsaturation. So if we have, in order to have a trans fat, we have to have something that is unsaturated. And when we talk about trans fats, we're really looking at the location of these two bonds opposite the double bond. If they're on opposite sides like this is going to be considered a trans fat. If they're on the same side, right? So if this rotates around and both of these bonds come up, that would be a cis fat. The trans fats, because of they sort of become linear, are going to act much more similar to these ideas of saturated fats. The cis fats are going to cause more disruption, and it's going to be much more of a liquid. It's going to be a much more unstable arrangement if we have this. The trans fats, though, are easier to break down because every time we have this place, we have much easier time getting in there to break apart that bond, which means that it's going to give us energy much more easily than this saturated. Right? There's a lot of debate on, I guess really not debate, a lot of studies that have shown that trans fats are bad for us, give us some harmful health effects, but it really comes down to this idea of saturation. Right? And fats are going to be spread all throughout the types of food as well as the cooking process. But one thing we need to remember about fats is that because they have a wide variety of chain lengths inside this triglyceride, these fatty acids could be different lengths. They're not going to have, unlike other things, they're not going to have a single melting point. These fats are going to melt over a wide range of temperatures, which is important for us because we take that into advantage when we make things. We can get things that are moist because some of the fats are going to be at certain temperatures. They're going to be liquids. Other ones are going to be solids. We talk about butter, for example. When we make cookies, one of the things that makes them nice and airy is the fact that we can get this butter that stays as a solid until we get to a higher temperature, and then it will liquefy, allowing us to get a more puffy cookie. But because of these broad melting points, and because these molecules are so large, their melting points are actually very high. Or their boiling points are. So when we're not able to actually transition most of these fats from liquids into the gas. And instead what happens is they break down. The heat is actually so much that the molecules start to break down and form smaller molecules, some of which are volatile, and produce what we call smoke. So each one of these oils is going to have a smoke point, a temperature at which that oil is going to begin to break down and begin to smoke. That's really important for us if we're frying foods, because we want a food to fry in an oil that has a fairly high smoke point, which is why you typically see a lot of oil or frying applications use things like peanut oil or sunflower oil, which have a larger smoke point than something like butter or olive oil, for example. Both of those have a fairly low smoke point so that we don't raise the temperature up too high before they start to break down, which can give us some off flavors, but it also is an irritant. When you're cooking this, if you get a lot of smoke coming out of your oil, you're going to get eye irritations and whatnot. But the most important thing is you're going to get an off flavor produced into your food. The other thing that we have to be concerned about with these fats is this idea of rancidity, which means that these unsaturated bonds, when they're exposed to oxygen, are going to react. And when they react, they're going to give us some off flavors in order that we associate with rancid food. Most of the time, that isn't harmful to us. Fats that have gone rancid could still be capable of being eaten. They just are unpleasant. We get an unpleasant aroma, unpleasant flavor. So we need to keep these fats cold and away from oxygen. So we're looking at this reaction with oxygen is what causes this rancid thing, and that is sped up as we increase temperature, which is why you typically will put some fats into the refrigerator, like butter, for example. Even though it doesn't have to be stored, it can be maintained longer by lowering that temperature. But the key point is that the more unsaturation you have in your fat, the more susceptible it is to rancidity. So we have to be aware of the amount of unsaturation in our fats, and that will correspond to the different types of fats. But because of these broad melting points, they're also going to be very helpful in giving us textures and flavors in a wide variety of food. Again, we'll spend some time in the lessons and in the lab dealing with these fats and seeing their interactions. The other thing that we should know about fats is that they are our primary storage for long-term energy. So we see that they store a tremendous amount of energy. So when we look at the caloric intake, 1 gram of a fat is going to give us more than 2 times the amount of calories that of a protein or a carbohydrate. So 9 calories for every gram of fat. So these are big, long things that give us a large amount of energy, and it really impact the flavor of our food. And the old saying goes, fat is the flavor. So just a simple introduction into fats. There's a lot more in the reading. Let me know if you have any questions.